Here we're told, determine the value of the series 16 plus 8 plus 4 plus 2 plus dot dot dot. And here this is actually an infinite geometric series. If you're wondering why, if we take the second term and we divide it by the first term, we get 2. If we take the third, 1/2. If we take the third term and we divide it by the second term, we get a half. If we take the third term and we divide it by the fourth term rather, and we divide it by the third term, we get a half as well. So here we have a geometric series where a is, let me use a different color here. We have a geometric series where a is equal to a is equal to, let's see here, a is equal to 16. A is the first term. R is equal to 1/2, and n is going to approach infinity. So we have n going to infinity because there's an infinite number of terms. This is an infinite series. So let's think about what happens when we actually have an infinite number of terms in this series. Well, we have that s, the value of the sum, is going to be equal to a, which is 16, times 1 minus r, and r is just a half here. So we have 1 minus 1/2 to the power of n. And let's just think about, let's not assign or substitute a value for n just quite yet. And that'll all be divided by 1 minus 1/2. Okay, and of course we can simplify this. So we have that 1 minus a half is just a half. If I divide 16 by a half, I get 32. So I have 32, and then I can distribute 32 into the brackets above, because I'd have 32 times 1 minus 1/2 to the power of n, which is equal to 32 minus 32 times 1/2 to the power of n. Now let's think about this. Let's think about what happens to the value of the sum as n approaches infinity. As we get more and more terms in this series, as we add more and more terms in this series, what happens to the value of the sum? Well, we're not going to prove why this is true in this video or offer any kind of rigorous explanation, but let's just think about this kind of based on our observations. If we have 32 minus 32 times 1/2 to the power of some really, really big number. So let's think about if first, if we have let's think if there's only like 10 terms in this series, what are we going to have? So we have 32 minus 32 times 1/2 to the power of 10. What's that going to be equivalent to? Well, we would get, if we actually perform that on our calculator, and we'll just round this for now, 32 minus 32 times 1/2 to the power of 10. We would get that this is equal to 31 and 31 30-seconds. Okay, so 31 and 31 over 2. And if we round that to a decimal, we would get 31.969. So this is approximately 31.969. Or I've just rounded it. Okay, so let's think about this for a second, and let's suppose that I have 32 minus 32 times 1/2 to the power, and let's say that I just used 30 terms now. Well, that would be equivalent to 32 minus 32 times 1/2 to the power of 30. And that would be equivalent to 32 minus 32 times 1/2 to the power of 30. And we get 31, if we approximate this, we get that the approximate value is 31.9999. Let's see, how many nines are there? 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7, and 7. Okay. So this is 31.999999997. So let's think about what's going to happen if n keeps increasing here. Well, if I raise 1/2 to an increasingly large exponent, then that means that the value here is getting increasingly smaller, because, like, let's say I raise 1/2 to the power of 40. Well, that's going to be 10 factors of a half smaller than 1/2 to the power of 30, which is already really, really, really small. So as n goes to infinity, we actually have that, or as I add an infinite number of terms, this second term is 30, becomes minus 32 times 1/2 to the power of some really, really large value, an infinitely large value. And if you raise 1/2 to the power of an infinitely large value, that value goes to 0. So we'd have 32 minus 32 times a value that's approaching 0. So what that means is that I've got 32 minus some an infinitesimally small value, which means that I'll just have 32. So as n goes to infinity, so as we let n go to infinity, we actually have 32 minus 32 times 1/2 to the power of an infinitely large number, and 1/2 to the power of an infinite n as n goes to infinity is actually 0. So I'd have minus 32 times 0, which is 0. And I'd have 32 minus 0. So the value of the sum is actually just 32. Now there's an important thing to note here. The important thing to note is that I actually get, by adding an infinite number of terms here, I get the value of the sum is the exact value of 32. And that's because the common ratio here is between 0 and 1. If the common ratio here were actually growing, such that each successive term was bigger than the last, the value of the sum would obviously continue to increase as I added more terms. But because the next successive term in the sequence, or the next consecutive term in the sequence, is smaller than the last, and I have this common ratio of 1/2. This series actually approaches some constant value as I add in more and more and more terms. So that's really interesting here, that we can actually sum an infinite number of terms when the common ratio is between 0 and 1. And we're actually going to come up with a formula if we have for an infinite geometric sequence where the absolute value of r is between 0 and 1. So we know that if we have a this should be let me change this. This should be a plus ar plus ar squared. Let's see what's going on here. Plus ar squared plus dot dot dot. Well, we know that the value of that sum, based on the formula that we derived previously, is equivalent to a times 1 minus r to the power of n, all divided by 1 minus r. And if r, the absolute value of r, is between 0 and 1, we can say that as n approaches infinity, r to the power of n is actually equal to 0. And let's think about why that's true. Well, here, if r is between 0 and 1, that means that it's you know, a number like 1/2 or 1/3 or you know, 3/4. It's a value that when I square it or I cube it, it's going to be smaller than just r to the power of 1. So let's suppose I have r squared, r cubed, r to the power of 4, r to the power of 5, dot dot dot. If r is between, if the absolute value of r is between 0 and 1, then I know that the absolute value of r squared is less than the absolute value of r. I know that the absolute value of r cubed is less than the absolute value of r squared, and so forth. So and as we raise r to the power if we have r to the power of n, where n is approaching infinity, this value of r to the value of n goes to 0. So it's actually equivalent to 0. So what that means is if we have an infinite number of terms, so as n approaches infinity, we have that s is equal to a times 1 minus 0, all divided by 1 minus r. So if we have this infinite geometric series where r is between, the absolute value of r is between 0 and 1, the value of the sum becomes a over 1 minus r. So we can sum an infinite number of terms. That's only if the absolute value of r is between 0 and 1. And that's because if r were greater than 1, or the absolute value of r was greater than 1, the next consecutive term would be greater than the previous term. So we'd get a series that we'd get what's called a diverging series. So that means that when you add more terms, the absolute value of your sum becomes larger and larger and larger. So it's pretty interesting that we can sum an infinite number of terms for a geometric series with a common ratio between whose absolute value is between 0 and 1 using this formula. It's really cool.